Let me introduce dynamic programming using a much simpler example. You all must be familiar with the Fibonacci series, right? Um, it's just a series of terms starting with 0 and going through 1, 1, 2, 3, 5 and so on, such that the nth term in the sequence is the sum of the previous two terms. Right? I presume you probably must have been exposed to this in either a discrete math class or uh, a basic algorithms class. Now, if you want to write a program to calculate the nth Fibonacci number, one way to write that, one way to implement or to design an algorithm is just to use the definition of the Fibonacci series and say that if I want to, if we have to calculate the nth Fibonacci number, I'm just going to say if n is equal to 0, then return 0. Okay. If n is equal to 1, return 1. Okay, I'm assuming, okay, let's actually call this 1 and 2. Okay, the first Fibonacci number is 0. The second Fibonacci number is 1. So this is the first number, first Fibonacci number. This is the second one. Now, if n is neither 1 nor 2, and if it's greater, I mean, I'm assuming that n is positive here. You can add that check. If n is greater than 2, then we'll just return fib of n minus 1 plus fib of n minus 2. Okay, this is just a simple way to this is a simple recursive algorithm for calculating the nth Fibonacci number. Now the problem with this algorithm is that if you try to analyze the complexity of this algorithm, you're going to find that in order to solve a problem of size n, okay, in order to calculate a problem of size n, you're dividing it into two problems of slightly smaller size. Okay, so let me just call this fib of n is going to call fib of n minus 1, and it's going to call fib of n minus 2 recursively. Now fib of n minus 1 in turn is going to call fib of n minus 2 and fib of n minus 3, and fib of n minus 2 is going to call fib of n minus 3 and fib of n minus 4, and so on. Fib of n minus 2 is going to call fib of n minus 3 and fib of n minus 4, and so on. Now if you implement this algorithm recursively, notice that you will be repeating the same kind of calculations over and over and over, because let's say in order to calculate fib of n minus 1, I need to calculate fib of n minus 2. Okay, and in order to calculate fib of n minus 2, I need to calculate fib of n minus 3. Now once I have calculated fib of n minus 3, my code is not, it's just going to use that value to calculate fib of n minus 2. But when I'm again going to call fib of n minus 3 over here, it's going to again repeat the whole work that I did over here to calculate fib of n minus 3. Likewise, you can see that fib of n minus 2 here will be repeating all this work denoted by this subtree that was done over here, because fib of n minus 2 is already calculated over here. But still I'll be calculating it all over again. So if you actually expand this tree all the way down to the base case, which is either n equal to 1 or n equal to 2. So the base case is either 0 or 1. Okay, so you will have leaves. At the leaf levels, you will have values of the Fibonacci number as either 0 or 1. and all the values at the leaves are going to be aggregated over higher and higher levels until you end up with the actual value of fib of n. Right, so all these zeros and ones will be added to one another successively until you calculate fib of n. So you can see that the complexity of this algorithm, the amount of work that you'll be doing, will be proportional to the number of nodes in this tree. And it turns out that Fibonacci numbers, fib of n grows proportional to, so it's exponential in n. Okay, so it's a to the power n for some a greater than 1. Okay, so you'll need to do an exponential amount of work in order to calculate fib of n. A much simpler way to calculate fib of n is to store partial solutions. And that's the idea behind dynamic programming. Store partial solutions to smaller problems. I don't know if you've done divide and conquer algorithms, but just as in divide and conquer, in dynamic programming also you divide a larger problem into smaller and smaller subproblems, just like we did over here. But divide and conquer tries to go top down, right? It tries to solve this problem first and then this problem first and then combine the solutions. And this was effectively a divide and conquer algorithm. But in dynamic programming, we will go bottom up. We will start from the smallest instances of the problem. And then we will build up the solution to larger and larger sub-problems using the solutions to the smaller sub-problems, which we will store. Okay, we won't repeat any work now. And the simplest way to do that, to go bottom up, is to start with the first two Fibonacci numbers. We don't need to calculate them because they're already given to us, 0 and 1. And now we'll go bottom up. So let's calculate what the problems, what Fibonacci of 3 is. It's just 0 plus 1, which is 1. What is Fibonacci of 4? It's just 1 plus 1, which is 2. What is Fibonacci of 5? It's just 1 plus 2, which is 3. What is Fibonacci of 6? It's just 2 plus 3, which is 5. So note that when I'm calculating Fibonacci, when I reach Fibonacci of n over here, I will have already calculated and stored the result of the values of Fibonacci of n minus 2 and n minus 1. And all I need to do in order to calculate Fibonacci of n is to just add these two numbers. Okay, I'm storing all the results up to this point. Of course, I don't need to store all the results because to calculate Fibonacci of n, I just need to know the values of the two previous subproblems. So once I calculate what Fibonacci of n is, I can actually discard this value if I am short of memory. But the idea here is to store these solutions to the smaller subproblems, to go bottom up and to store the partial solutions to smaller subproblems and use those partial solutions in calculating the solution to larger and larger problems. Now because of this storing, because of this extra memory that we'll be using, we will actually cut down on the amount of time needed to calculate Fibonacci of n. So the amount of time needed to calculate Fibonacci of n will just be big O of n, because it just takes a constant amount of time to calculate Fibonacci of n. It's just a single addition, and so we'll be doing n such additions by the time we come to a problem of size n. So the total time taken will be big O of n. So are you familiar with the big O notation and algorithms like this? Does this make sense, or this is the simplest possible example of dynamic programming to convey what dynamic programming does? Any questions about this?
No, sir.